This video will walk us through the three main expressions of solution concentration that we use in honors chemistry: molarity, molality, and percent composition by mass. By the end of this, you will have an understanding of how they compare to each other and what are the types of problems where we'll be applying them. So let's dig in. Molarity is represented by a capital M. Molarity is found by evaluating the moles of solute per liter of solution. Usually, we're trying to reference, with solution concentration, the ratio of solute per solvent or solution. So this is molarity. Molarity is the go-to solution concentration expression for chemists because it communicates concentration in mole of solute. So that can get us right to stoichiometry or simple calculations per liter of solution. And most solutions are in the liquid state, and we'll be measuring them in terms of milliliters or liters. So this is really the most practical solution concentration expression. But we will also work with molality, which is represented by a lowercase m. And molality is mole of solute, but that is per kilogram of solvent alone. And we'll usually just work with molality primarily when we talk about colligative properties at the end of our chapter. We've already had some experience with percent composition, primarily with formulas. Well, a percent composition is always going to be a mass ratio unless otherwise noted. And when we're using it in terms of a solution, it will be the mass of solute over the mass of solution. And we need to realize that is, of course, the solute plus the solvent. Now, it would be fine if you just wrote mass of solution. We just have to be aware that sometimes we're given the mass of the solution and sometimes we're given solute and solvent. So oftentimes representing this separately will help us avoid mistakes. We, of course, multiply by 100 to make it a percentage. Of course, we will be obeying significant figures with all of these. So let's dig into some sample calculations. First, molarity. We will encourage you to apply dimensional analysis or unit conversion instead of simply manipulating the formulas. Let's show this at work. What if we're asked to find molarity given mass of solute and volume of solution? All right, we have to know what our concentration expressions reveal. And of course, we'll provide these, you won't have to memorize. Molarity, remember, is mole of solute per liter of solution. So as long as we set up our calculation so that we end up with these units, we are good to go. Well, I know I want solute in my numerator, but I want moles, not grams. But I know if I start with grams, I can get moles. So I'm going to start my dimensional analysis with that because that will automatically put my solute in the numerator. This is my volume of solution, which I want in the denominator. So it doesn't make sense to start with that in the numerator. So let's dig in. If you want to put this over 1, you definitely can. So we know we need moles of solute, and finding the formula mass, sodium chloride is 58.44 grams in every 1 mole. Okay, I've gotten my numerator. Now, I just need liter of solution in my denominator. We never hesitate to put a number over 1, but for some reason we hesitate putting a number under 1. But that is fine in this case, because what will happen when I do all of my math, I will get mole of sodium chloride per liter of solution, and that is the expression for molarity. So when I work out my math, I'm allowed 3 sig figs. This will be 0.589. Now my units end up being mole of NaCl, which we always want to reference what our solute is, per liter of solution. You can leave this, but we can also understand that mole of solute per liter of solution is molarity. So another way we could write this is 0.589 big M NaCl. That is our answer. All right, let's move on. How many moles of NaCl are contained in this volume of the solution? All right, I want moles of NaCl at the end. Okay, I'm starting with this volume and I'm now referring to this 0.589 molar solution that I found. Now remember, molarity means mole of solute per liter of solution. So I can expand that concentration to be a conversion factor. I'm going to write that as 1.00 liters to respect the 3 sig figs that I found. So I have this given and this given. We know when we have more than one given, we usually want to start with our simpler given, our non-conversion factor. So let's see. If I start with 0.0100 liters of my NaCl solution, I put my expression for molarity, and look at that. Using molarity as a conversion factor, I get my moles of NaCl. All right, one more example with molarity. Well, what if again we have this same solution? And so it's that 0.589 molar solution that we found in part A. So now we're asked for volume if we had 0.2 moles of NaCl. So I know I can write this as a conversion factor. So I'm going to start with my simpler given, 0.200 moles of NaCl. Okay, I want volume of my solution in the numerator. I need to cancel moles of NaCl. And I know, per this solution, there's 0.589 moles in every 1 liter. So, doing the math, moles cancel, and then I have 0.340 liters of the NaCl solution. So, those are some example molarity problems. All right, now let's look at some sample molality. All right. Now, how will we know that a problem involves molality, not molarity? Well, we have to be able to really distinguish. I know that they name them so similarly, but molality. So it's either going to outright read molality or molarity, or it will give us the concentration in terms of a lowercase m. Then we know we're dealing with molality. Okay, again, to dig in. So what is the molality when 328 grams of sodium chloride are dissolved in 3.50 kilograms of water? Remember, molality is mole of solute, but that is per kilogram of solvent. Now, I know that water is usually my solvent, but remember, your solute will be in the lower quantity compared to the solvent. So that's just another way to check. Just wanted to remind us of that. We'll encourage you, instead of, solving the formula, to set it up with dimensional analysis. Now, I know I want the solute in my numerator. So, 328 grams of NaCl. And I know I want it to be in moles, so 58.44 grams of NaCl in every 1 mole of NaCl. But now, for molality, that will be per kilogram of water in this case, which is my solvent. So, when I do my math, I will get the units in the numerator and denominator for molality. And the answer that we got was 6 sig figs, 1.60. I could write mole of NaCl over kilogram of water, or just lowercase m. And I must indicate the solute. Okay, what if we're given the concentration in molality and then the mass of our solvent? We want grams of ethylene glycol. Now we know that we can express this as a conversion factor. So I'm going to start with my kilograms of solvent. And I know expressing this, every 1 kilogram of solvent, which is water here, I have 3.50 moles of ethylene glycol, C2H6O2. That'll give me moles, but it's asking me for grams. And every 1 mole of C2H6O2 is 62.08 grams. And when I do this calculation to 3 sig figs, 1,090. So remember, captive will be significant, trailing is not unless I put a decimal, and I will not, and that's grams of C2H6O2. Okay, so 2 examples of molality. Now let's look at percent composition. Can we imagine that this problem reads what I've rewritten? So what if it asks for the concentration in percent composition of 4.80 grams of citric acid dissolved in 120 grams of water? And they're giving us the molar mass of citric acid. We may need that. Well, percent composition, remember, is mass of solute per mass of solute plus mass of solvent times 100. So we are given 4.80 grams of the citric acid. I could write the name or I could write the formula divided by, and this is where we just have to be careful. It will be 4.80 grams of the citric acid plus the grams of water. I am fine if you just added that separately and you put 480 grams of citric acid over, and you did this separate on your calculator or mentally, 124.8 grams, and that would be solution. We have to be on guard to make sure the units all are in agreement. They're all in grams, they're all in kilograms. If they weren't, we'd have to convert. But also respecting sig figs. Remember, when we add, we report the least precise decimal place. So I would go ahead and do this division times 100, and we would get a solution that is 3.85%, and we could write citric acid, or go ahead and write the formula, C6H8O7. Either is fine. Okay, next example. What if we were asked to find the grams of sugar that were in 125 grams of a drink that was 10.5% sugar? Okay, so here's 125 grams of the soft drink. We know we can express a percent as a conversion factor. We did that way back when with complex givens and stoichiometry problems. So let's dig in. 125 grams of this drink, which I'm going to go ahead and call it a solution. And I know that for every 100 grams of the solution, I have 10.5 grams of sugar. Remember, that's how we can express a percent as a ratio out of 100. And us knowing how percent composition really is, we can translate this as that expression. And look at that. That will give us the mass of sugar. And so, the answer that we should get with 3 sig figs is 13.1 grams. So that's just a couple examples of percent composition. Now, there's one more form of equation that we can apply. So, molarity, molality, percent composition. But there is one more. The dilution equation. M1 V1 equals M2 V2. All right, so where does this come into play? Okay. Imagine, ladies and gentlemen, that you were asked this question. You want to make 500 milliliters of a 2 molar sulfuric acid solution. In your supply, you have a 15 molar stock solution of sulfuric acid. So imagine back in your storage, you have a 15 molar sulfuric acid. Often, solutions that are kept in storage of higher concentration, and we pull from these and dilute them to make lab solutions. We often call those stock solutions. Now, we want to make a 2 molar sulfuric acid solution, and we want 500 milliliters of this solution. This is the volume, and this is the molarity. It's what I'm trying to make. So I'm going to call that molarity 2 and volume 2, where here is my starting concentration. So what I need to find is what volume of this do I need to measure out, add water to make a lower concentration. You know, imagine that you purchase some orange juice in the store and you take a drink, and it's so concentrated. It's really sweet or just really powerful in its flavor. Well, you know you can add water to decrease the concentration or dilute it, and that's what we're doing in this case. So, if we apply M1V1 equals M2V2, we are trying to find our second volume. Given what we're given in the problem, we'll go ahead and plug in our values. Now, we know that molarity is mole per liter of solution. So is it okay that our volume is in, I'm going backwards. Goodness gracious. Please forgive my error, ladies and gentlemen. I'm so sorry that I referred to the incorrect work. All right, so what we're trying to find is V1. You know, I like to rearrange my equation. Okay, so we're trying to make a 2 molar and 500 milliliters of it, and our stock solution is 15 molar. Okay, is it all right if our volume is in milliliters? Absolutely. These units cancel, and so your volume unit, as long as you don't need volumes to cancel, they can be in any unit, milliliter or liter practically. All right, so when we do our math, what we get is 66.7 milliliters. But milliliters of what? We were solving for V1, which matches the stock solution. So we need 66.7 milliliters of the 15 molar sulfuric acid solution. But what do we do with that? Do we just simply take a grad cylinder, measure our 66.7 milliliters, and then we have our 2 molar solution? Well, of course not. We need to add water. But how do we know how much water? We already were given that we are trying to make a 500 milliliter solution that is 2 molar. that is our V2. So if we subtract the total volume we're shooting for, or if we take the amount of stock solution from the total amount we're shooting for, we'll get the amount of water that we had to add. So, being careful with sig figs, and we can report to the 10th, and we're going to have to add 433.3 milliliters of water. So you may be asked, how would you make this? What is the recipe? So according to the way problem 1 was worded, this is our answer. But if you would be asked, how would you make, what is the recipe, you would write that you would add 433.3 milliliters of water. So, ladies and gentlemen, here are 2 more examples using the dilution equation. So, here's the problem, and here's my work. And then here is another, and that was mistakenly the one that I started to show you before. Now, I would say 85% of the time, ladies and gentlemen, we are going to be asked a problem like I did first. And that's why I took the time to go through this. Because, ladies and gentlemen, that's the majority of time what Mrs. Kendrick and Mr. Orelli and I end up solving when we're trying to make dilute solutions from our stock solutions for us in lab. So this is practically, the information that we need. So that gives you an overview of solution concentration expressions. Best of luck employing these equations.